All right, welcome back. This is lesson 7. This is going to be essentially the last lesson of this unit booklet. We're not really going to go into lesson 8 and 9. The titration lesson we'll do in the class and in the lab. So we won't worry too much about that. We've already done a lab on it at this point anyways. So we're just going to focus in on what does it mean for an acid to be weak. Well, and think about that in terms of equilibrium. So the acid dissociation constant, this is a special K, just like KEQ and KSP. We have a Ka specifically for acids. Because liquids are pure, we can arrange our products over our reactants and then get rid of the H2O. What I really like about dealing with Ka, and one of the things I almost feel like we could even start with this unit and do just as well, as opposed to starting with with equilibrium that could get more complicated, is that these reactions are almost always single proton transfer reactions. We don't think about Kas as more than one proton at a time being donated, so all of your exponents will always be 1. So these will always be 1. That saves you a lot of mathematical problems. And then the other benefit of working in Ka is that Ka is often so small that we don't have to worry about the changes to our original concentration. So I'll show you what that means in a few minutes. Ka is great. It's a really powerful tool if you go farther into chemistry. We used Ka quite a bit in organic chemistry. If you knew the Ka of various functional groups, you could figure out which functional group was most reactive and which functional group was less reactive, and all sorts of interesting things. So it's a really useful measurement because it's essentially the measurement of the relative acid strength, and this also correlates well with bond strength. So maybe we'll just add a little note here. So Ka also correlates with bond strength to hydrogen. Larger Ka have weaker hydrogen bonds, more dissociation. Lower Ka equals stronger hydrogen bonds. So in a chemistry class, we would often look at something like this. Let's go back to our acetic acid we just talked about here. And so in acetic acid, a student might be interested in saying like, well, what about if we compare this hydrogen over here and this hydrogen over here? And we would find that probably we can look these numbers up, and there's actually little tables that you can use in organic chemistry. This Ka is really large, or relatively large. Okay, it's 10 to the, well, it's acetic acid, so I think it's, I can't even guess, but we could probably look it up if we had to. And actually, it's probably on a table, or we have acetic acid, I think, in this question. So here's the acetic acid one. So it's oh, that's not the K. Yeah, that's K. Okay, so 10 to the negative, or no, here's my answer, 10 to the negative 5. So it'd be something like 10 to the negative 5, and then the other Ka would be in super small. So this Ka will be, I don't know what I'm doing here. Let's just call this Ka1, and we'll just do Ka2 and so this Ka2. And so somebody who's an organic chemist, they'd be interested in comparing, and they would say that Ka1 is much bigger than Ka2. And so if there's a base nearby, which of the protons is leaving? It's always going to be the one with the higher Ka. So anyways, that's a sidetrack. Let's get into it. You can also create a Kb. This is simply an equilibrium expression that has a base in it. You're always going to have a hydroxide up here, and then you'll have the other parts. Good news is that in this course, we're almost exclusively going to be using ammonia. That's just how things shake out. There aren't quite that many weak bases that we can use So it'll be ammonium or some generic base probably. So here's an example. Kb of ammonium is 10 to the negative 5. This means that this is the general sort of proportion of how much product is produced for each unit of reactant. Nearly all hydroxide bases are strong bases, so we don't do any Kb calculations for those. If we do go back to our KSP table, we'll notice that some of those hydroxides, but most hydroxides are soluble with a few exceptions, calcium, magnesium, etc. Okay, so how do we use this? Really, the only thing we're doing is we're doing a brand new, we're doing what looks like new work, but is in fact a lot less. It's a lot of the same stuff that we've done in the past. So let me just sort of build out some hidden sections here. And okay, let's hope I can remember where they are. So this question asks that initially at 0.1 molar solution of acetic acid is only partially ionized. If at equilibrium the hydronium ion concentration is 1.3 times 10 to the negative 3 molar, what is the acid dissociation constant Ka? So if you're playing along at home, you'll realize that these are this is a KEQ question that we did weeks ago. It's a very, very similar question to a KEQ question that we did quite a long time ago. But let's see what happens as we go along. So CH3COOH, this is going to be dissociating into these two products. That's good enough. We could rewrite the reaction with water if you wanted. If you want to put water in, that's no problem. The only change is we're going to replace this with C3O+. That's the big change. If that is great if that works better for you, then go for it. I've already formatted the rest of this around this ionization sort of picture, but otherwise it's fine. So if it's a KEQ question, then we can really just do the old ICE table. So I'm gonna just do some little hiding here. So I'm gonna hide this and I'm gonna hide that. Okay, so here is my KEQ table. Initially I had a certain molarity, right? I have a molarity of this molarity of solution of acetic acid, and later on I have this molarity. So I set that up in my table. That's the molarity of my hydronium ion, or in this case H+, proton ion concentration. So here's my initial concentration, 0.1. Here's my final concentration of hydronium. Both things were given to me in the table. We know that the change must be a change of X, and there must be an equal amount of CH3COO- that's produced. Otherwise, it wouldn't work out. It has to follow the stoichiometry. So then that tells us what X is, because if you go from 0 to 1.3 times 10 to the negative 3, then X must have been 1.3 times 10 to the negative 3. If X is 1.3 times 10 to the negative 3, then that means the final concentration of CH3COO- is 1.3 times 10 to the negative 3. Looks like I'm missing a 0.3 here. Ooh, too big. All right. 1.3. There we go. And if that's what X is, then we can also erase this one here. And we can subtract this from our 0.1 to get our final value. So here's our final values, or equilibrium values, of the three components of the solution. No water included, of course. And then somewhere over here, yeah, there it is. I can write out my Ka expression, fill in the Ka expression, and then solve, and that's my Ka. So that's the exact same sort of equilibrium constant question we did in the previous unit, or 2 units ago. The only trick here is that we're just dealing with acids. So in fact, this is kind of a boring question to me. I don't know if I'm actually that interested in you being able to do this question, because you've already done KEQ questions that were much more difficult because they had different exponents. But, never say never. All right, so here's where things can be more difficult. So I'm going to, again, do a little bit of erasing here. Be a little bit careful. Get rid of that. All right, so HA is a weak acid. It has a Ka, so this is a different question because we're given the Ka value. Also very, very similar to something we did just 2 units ago. What is the concentration of all species if the initial concentration is 0.5? So you've got the word initial, so you're making a table. So here's my ICE table. I'm putting in my initial value here. This is the value they gave you in the question, and then I'm giving my initial values of hydronium and acid. We're just going to assume those are 0. It's always a 1-to-1 ratio in these questions, so we know we're going up by x, we're going down by x, and we take our value and we have a value here and these 2 values down here. So once you have equilibrium values or some expression for the equilibrium values and you don't know anything else, you don't have any real numbers, then you need to go to your Ka expression. So write out your Ka expression, fill in the Ka expression using the values that they've given you. They did give us the Ka. And then from here, you got a couple options. I'm going to show you the easiest one for me, which is simply get out my phone and use something like Photomath to take a picture of this equation and give myself an answer. All right, so that's kind of a boring, that's the quick route. It's not nearly mathematical or anything interesting. Certainly an expansion here, following some algebra, you could create an equation. Ooh, forgot about that. So you could create a quadratic equation, quadratic formula, but either way you're going to get to something like 1.2. And then you can plug that in and replace the x values. But look what happens over here. This is what I'm interested in, is that when the numbers are so small, especially when you're dealing with an exponent that is more than -5, around 10 to the -5 and more, as long as you're dealing with fairly high concentrations of solution. So high concentrations means at least that's around 1, or more than 10 to the -3 difference or so. When you're dealing with very strong concentrations but very weak acids, you'll notice that there's almost no change to that concentration. It's a little bit strange to wrap your head around that you are producing products, but they are within the error of the measurement of the concentration of the starting material. So this means that if we're essentially saying that there's been no change relative to the size of this value, there's been no change, we could approximate that x is essentially 0 for this question. Or at least with respect to 0.5. And that means that we could just straight up right away say that this is 0.50 and then calculate for x. So I'll show you what that looks like. Over here, what I've done is I took what was supposed to be here, right? There was supposed to be a negative x here, but I said, you know what, this is so small, it's not going to have any effect on the 0.5. I then do some calculation. You can use algebra here and use a quadratic formula. I again use Photomath probably, but the answer here from algebra will give you 1.9 times 10 to the -4. They're close. It's not, they're not super duper close, but I think that you would find that, there we go, that's what I was looking for. if we took 1.9 times, or actually let's take the real value, 1.2 times 10 to the power of negative 4, correct? Negative 4. And let's just divide that by 1.9 times 10 to the negative 9. Oops. Actually, we should take the difference. So we could find let's say like a percent error. So 1.9 times 10 to the power of negative 4. And you know, I'm doing so much more work than I need to divide that by our real number, 10 to the power of negative 4, and I need to put some brackets in. You know, this is just a lot of math. This is something we did a lot of back in the day. So we're, you know, that's 50% error. That's actually kind of high, 58%. So that may be more of an estimate than we want. There is a strategy here where you could punch this estimate into the equation again, punch it into here, and try again and see what the value you got on the second round. But I'm happy with this either way. Either way, if I saw you do an estimate, I would be just pleased that you're able to do it, and this also saves you some hassle in terms of having to use an app or something to solve your equation. This is much easier to do by algebra than this one, at least. Okay. The next section is about percent dissociation. I don't really want to get into this. I will give you some notes about this right now, but I'm not even going to mention this in class. So I'm just going to leave it on this video in case you're really gung-ho about it. I think it's just more effort than we need, and we don't really use it that often in experiment. So calculate the percent dissociation of a 0.1 molar solution of formic acid if the hydronium ion concentration is this much. So what they're suggesting is that you take the amount of your initial solution and the amount of hydronium, and you divide them and multiply by 100%. So here we go. This is what we did. We took the amount of hydronium on top, the amount of initial solution on the bottom, divide, multiply by 100, and you've got your percent dissociation. I don't know. I mean, it's an easier equation, but it might have some value. I don't see the application that often. It gets pretty. You can create some pretty interesting and complicated problems if you want. Here's an example of one that I think is beyond what we really need to get the point. So here we have a question that uses percent dissociation. So let me just get in here, do some edits here to hide some things from us. Okay. All right, so here they said calculate the Kb of a hydrogen phosphate ion if a 0.25 molar solution of sodium hydrogen phosphate is associated at 0.08%. So they do some interesting stuff. You take the 0.08, you times that by your initial concentration to figure out how much H plus you produced, or how much hydroxide you produce. Technically, I guess this is hydroxide here, probably over here, but it should be the same value for both of them. So we can put that value in both slots. This tells us that the amount of change, or x, is equivalent to this value. So either one of these values is equivalent to this value just calculated. Now that you have the percent dissociation, you can figure out how much is left of your original value. So you can subtract this 2 times 10 to the negative 4, and that will leave you with your new concentration. So this is the new concentration of your starting material, your HPO4. Notice that this is a Kb that they're giving us. So Kb means this is the amount of base action. So we have to think about we had to think of an equation that produces an OH. So notice I did not choose to donate the proton. I didn't treat it as an acid. I treat it as a base. This is because it's Kb. And then we take these four values and we punch that into a Kb equation, which seems to be missing its R here. So give me a Kb, products over reactants, punch in the values, and you can determine the Kb. So I think this is most useful in an experimental sense. To determine percent dissociation, this could actually be measured by the electrolytic nature of the solution. So if you could measure measure how much conductivity you were getting from a solution, then that would tell you how many ions are in the solution. And then that would tell you what percentage of the solution was dissociated based on your initial values. And then you could work that backwards into a Kb. So, Kb is not a value you can just measure directly. So it's interesting from an experimental point of view. I don't think we're actually going to do much with it. And this one I just sort of stopped at a certain point. So what is the pH of an imaginary acid? Oh, actually, let's do this question together. So what is the pH of an imaginary acid, HA, if the initial concentration of acid is 0.1 and the Ka is 10 to the negative 9? All right, so I set up my equation. I have only one value and I have a Ka, so I'm going to have to do some work here. I'm going to replace my Ka in my expression with the value given. I'm going to replace those H and A's with the X's given. And then I'm going to replace the bottom with the expression given. This is a value you could put this into, Wolfram alpha or any of the equation solvers. That would certainly solve our problem. I want to do this the hard way, or the easy way, I guess. So I'm going to make a little box here, or I don't know how I want to enter. I'm going to just do this. 0.10 minus x is going to be equivalent to 0.10. So this is anytime you're doing an equation or a reaction like this, you can write assumptions at any point. So I'm going to write a little assume, and then I'm going to rewrite. So 4.0 times 10 to the negative 9 equals, I'm going to combine x squared divided by 0.10. Well, that's great, because now I can cross multiply. I can do 4.0 times 10 to the negative 9, and I'm going to multiply that by 0.10, and that'll give me still x squared. Eventually I'm going to take the square root of those, and then I'm going to pull up that calculator again and see how I do. Okay, so give me a square root. Give me 4 times 10 to the power of negative 9 times 0.1. And we get, nice, that's a nice round number to work with, 2 times 10 to the negative 5, and that's equal to x. 2 times 10 to the negative 5, if you took, so let's keep that answer. So if we did 0.1 minus 2 times 10 to the negative 5, I mean, look at that number, 0.099998. We might as well write 0.1, especially in a situation where we only have two significant figures. So it really has no effect on this concentration, although it is important to know how much H plus you have, right? So this is 2 times 10 to the negative 5, 2 times 10 to the negative 5. Great. All right, so that's not the question though, right? The question was pH. So to find pH, we need this concentration. pH equals negative log of the concentration of H plus. So let's do that right now. pH equals negative log of 2 times 10 to the negative 5. We can make a prediction. The pH should be in the 4 range. 4 to 6, so let's see what we get. Negative log of 2 times 10 to the power of negative 5. And we get Yeah, 4.7. There we go. And we're done. So that's a great little question. I like this one a lot. I like this is a good question to be practicing. And well, we might just do one more, I guess. Let's set it up. This is the carbonate ions, which are acting as a base. And it is asking about pH. So you know what? I do like this question a lot. So let's put some water in there. We're gonna the carbonate will take on one of those hydrogens. Oops, it's not gonna be 2 anymore, and it's gonna produce some OH ions. Okay, I'm not gonna put my phase symbols because I do want to go a little bit quicker here. We have initial concentration. We're gonna be subtracting some x's. We're gonna get 0.220 minus x, and you know what? I realize now that I lied and said earlier that we were always going to do ammonium, but this certainly is not ammonium, is it? Okay, and then the pH of a solution of 0.2 molar solution of CO3 2 minus ions is 10.75. What is the Kb of the carbonate ions? Okay, so I've got my system set up, and this is interesting. What could I do with this? This is a value for pH. That's not very useful. All right, so I'm hoping you all are screaming at your screen because you know that the pH plus the pOH has to be equal to 14. So 14 is equal to 10.75 plus pOH. Well, why do I care about pOH so much? Well, let's think about it. Let's think that we have 3.25 equals pOH. And 10 to the negative pOH is equal to the concentration of OH. So this is sort of a separate thing. So 10 to the negative 3.25 is equal to the concentration of OH, which means that it's equal, that if we get our calculators, 10 to the power of negative 3.25 equals okay, we'll call that 5.6 times 10 to the negative 4. That's a pretty significant amount of OH ions. And so that becomes the amount of OH ions. So that must be the equilibrium position of these OH ions. And that must be how many we get from this. I'm going to just change colors so we can show 0.20 minus 5.6 times 10 to the negative 4, which is going to give us let's do that over here. 0.2 minus equals, well, almost no change, right? So 0.199. 4. We are doing some calculation here, so we could leave it as 1.994 until we're done. We don't have to round right away. We can see that that's almost nothing. So the Kb expression is HCO3 minus times OH minus divided by CO3 minus. It's CO3 2 minus. Okay, and so I take my 5.6. If you're really lazy, you can just realize that both those numbers are the same, so they can be squared. And this exact concentration on the bottom, and that will give us our Kb. So equals, I like this app because I can do that sort of thing. And I'm going to do 5.6 times 10 to the power of negative 4 squared divided equals 1.57 times 10 to the negative 6. 10 to the negative 6 equals Kb. This is bugging me. I want to try to show good math behavior. Try not to do any flip-flopping if I can, and even if you're really precise, you should keep your equal signs in the right spot. I taught math a couple of years, and now I feel like I have to follow the rules. And there's your KB. So that's a really fun and interesting question. Hopefully you had fun too. We went from from having a value for pH all the way to a KB. That's pretty crazy. I think that's pretty wild. If you can wrap your head around that one, then you really are catching on to these concepts quite well. All right, best of luck with your studying. This is the last one for this series. The next lesson is on hydrolysis, and we're gonna just leave that alone. This is essentially the idea that because you are creating salts in this neutralization, then there is some interaction between different salts, and different salts can even produce acidic or basic solutions. But I think we're going to leave it there. That lesson gets pretty deep and heavy. So yeah, that's it.